In this video, we will do examples of calculating the net force. The important thing to remember is net means resultant, or the sum of, or sum of the forces. And it is this net force that determines motion, not the individual forces. So we have to calculate the net force before we can figure out how anything is going to move. So a lot of examples will just make it clear, I hope. Say we have a box and someone is pulling on the box with a force of 60 newtons to the right, and maybe there's a force of friction of 20 newtons to the left. What is the net force on that box in the x direction? Well, you can probably do it in your head. 60 minus 20 is 40 newtons to the right. So F net is forces to the right in the x direction. Forces to the right minus forces to the left. Now you will see this done differently. You will see the sum of the forces in the x direction, and then they'll just say any force to the left has a negative value. But I just like to look at it and say right minus left. So this would just be 60 newtons minus 20 newtons. Now, if the answer is positive, this tells you that the net force is to the right. That doesn't always have to be to the right. We may have a situation where somebody's pulling in the other direction. Say somebody's pulling this way with 70 newtons, and then there's only a force, say, of 10 newtons. Well, this F net in the x direction is you still go right minus left, 10 minus 70. So it'd be negative 60 newtons. And this tells you that the net force is to the left. And if there were no other forces acting on that object in the x direction, that thing would move to the left. Okay, it works the same way with up and down. So if we have an object, say it's just in midair, and maybe it has a parachute on it, so there's a force up of 60 newtons, and then maybe the force of gravity is only 20 newtons. Well, the net force in the y direction is up forces minus down forces. And so this would be 60 newtons up minus 20 newtons down, and this net force would be 40 newtons, and because it's positive, that would be up if we're talking about the y direction. And if we had more force down than up, so maybe something was in the air and it had a huge force of gravity of 100 newtons, and maybe just a little bit of air resistance of 20 newtons, well, the net force in the y direction then would be up minus down, negative 80. And this tells you the net force is down. And if nothing else is acting, that thing would continue on down. Now, it doesn't just have to be one force. You could have a whole bunch of forces. You may have, say, two forces this way and one force this way. So if this were 20 and this were 30 and this were 10, that's okay. You still go right minus left. So F net x would still be 20 plus 30 minus 10. So 40 newtons to the right. You don't have to put to the right, but you could put to the right if you want to make it really clear. The positive tells you it's to the right. Okay, so that's pretty easy when the forces are up, down, left, and right. What if they're not up, down, left, and right? What if we have something where there's a force off at an angle like this of, say, 100 newtons. And then maybe there's a force here of 20 newtons. And then let's put a force here of 30 newtons. Now, how do we get the net force? Well, you cannot deal with a force like this at an angle because that's neither up, down, left, nor right. You must break that into components. And this is why we spent all that time learning the trigonometry of right-angled triangles and how to find the components of vectors. So it's real important that you put your x and y axes so that we know which is x and which is y. Okay, so there's x, there's y. Now remember our trigonometry. A vector has two components, an x component. Now we'd have to be given an angle. So let's say this is 30 degrees. This, and this, we'll call this F, applied. So say that's somebody pulling on something. So this would be Fx. And remember, this side is close to that 30 degrees. So this would be F times cosine of 30 degrees. So that would be 100 newtons times the cos of 30, which I think is, that would be 86.6. Let's quickly punch that out. Yeah, that'd be 86.6 newtons. And then it has a y component. Now, I could put the y component over here, Fy, but because it looks nicer when we're doing up, down, left, right, put it in the middle of the box over here, and this will be Fy. That would be F sine 30 degrees, which would be 100 newtons times the sine of 30 degrees, and that will be 50 newtons. Now, once we've got those two components, just to make our diagram look a little better, we can get rid of that 100 Newton force in an angle. We've dealt with it. We've got its two effects. Its effects are it's pulling to the right with a force of 86.6. It's pulling up with a force of 50. There is some other force, 30 down, and then another force again, 20 left. So when we go F net x, right minus left, 86.6 minus 20 is 66.6. That will be to the right. F net y, up minus down, 50 minus 30 would be 20 newtons. Okay, so that's how you deal with those. Now, let's do a little bit more complicated one. What if we were told, oh no, I don't know why that happened. Okay, what if we were told that a box is sitting on a surface and somebody is pulling up on this box with a force of 20 newtons, and the force of gravity on the box is, say, 60 newtons. And then we're told the forces in the y direction must balance. So up has to equal down because the box is sitting on a surface and it's not going anywhere. So what force is needed to balance this downward force of gravity? Well, it has to be up. And it would be the normal force. And we're trying to find out what that normal force would have to be so that the two forces up balance the force down. Well, you can just do it in your head that obviously it's got to be 40 because 40 plus 20 equals 60. So if we're told that F net y equals 0, this means up forces must equal the down forces, because up minus down would be 0. So we will do a lot more of this when we do equilibrium problems in a future chapter, but we're going to need to know this about the normal force, that the normal force will just be what it needs to be to keep the box from falling through a surface. And so in this case, if up equals down, it means the normal force plus the 20 must exactly equal the 60. And that is how you get the normal force, would be then 60 minus 20, 40 newtons. Okay, so that's an important fact about normal forces. Okay, so let's do a fairly complicated one that you're going to have on your next assignment, and that is we have a box and someone's pulling at an angle, and it's a 40 Newton force. So this is the applied force, and it's 40 newtons. And our XY axes are going to be like this, X, Y, and this angle will be 30 degrees. And there's friction. The question is, find the net force in the X direction. And you're given coefficient of friction, mu K, is 0.4. And then you also have to be told the mass of the box. So you're also given that M box is equal to 3 kilograms. And that's all you need to be given. How much, so this would be like some child pulling a sled across a driveway or something. All right, so given the mass of the box, we will put the force of gravity on there. Force of gravity, mg. So 3 times 9.8, so be 3 kilograms times 9.8 newtons per kilogram, and that will give a force of gravity of 29.4 newtons. Okay, now there'll be a normal force on the box. We don't know what it is yet. It is not equal to 29.4 newtons. And the reason that it's not equal to that is because this applied force has a component in the y direction that's going to help the surface keep the box from falling through. So the normal force does not have to be as big as 29.4. But if it's being dragged along, there'll be friction. We have to assume that they're applying a force big enough to actually drag it. If the force isn't big enough to overcome static friction, then it's not going to go anywhere. Okay, so we have to get that applied force into its components in order to figure out the normal. So step 1 is find x and y components of applied force. Okay, so F applied x would be F cosine theta, because that's the angle given close to the x-axis. So this would be the 40 newtons times the cos of 30 degrees, and that turns out to be 34.6 newtons. The applied y component, F sine theta, is 40 newtons times the sine of 30 degrees. And that was 20 newtons. Okay, step 2, redraw the free body diagram with only x and y forces. Don't put the force at an angle anymore because that's too messy. So what do we have? We know we have a normal. We know we have that y component of the applied force. That's the 20 newtons. We have the x component of the applied force. That's the 34.6 newtons. We have the force of gravity, 29.4 newtons. And we have the force of friction. Now we don't know the force of friction and we don't know the normal force yet, but we can figure that out. So step 3, if no net force in y direction, then calculate unknowns. So if you know there's no net force, you know up has to equal down. If it said there's no net force in the x direction, then you know friction has to equal 34.6. We didn't say that yet. But when things are sitting on a surface, if they're sitting on the surface, like they're not flying off the surface or caving in, then there's no net force in the y direction. So we know that up equals down. Okay, so this is up equals down. That's only when the net force is 0 in that direction, only that direction. Don't do it for the whole thing. Okay, so obviously the normal force, 29.4 minus 20 would be 9.4 newtons. Okay, so step 4 is to calculate friction. And we have a formula for friction. The force of friction is the coefficient times the normal. And you can see how if you didn't take off that component of the applied force in the y direction, you get a way bigger friction force. So pulling up at an angle on an object tends to reduce friction because you're lifting it off the surface a little bit as well. So if you want to reduce friction on something real sticky, don't push horizontally, tend to pull up at an angle. Okay, we have a coefficient, it's 0.4. Now we have a normal force, 9.4. So the force of friction here is only 3.8 newtons. Okay, it's not very big. Now step 5, calculate F net X, which equals right minus left. And I'll just quickly sketch the right and left again. We have the X component of the applied force was 34.6. We've now got the force of friction, which is 3.8. And so F net X is 34.6 minus 3.8. And so that gives a net force in the X direction of 30.8 newtons. Okay, that thing would move over to the right. So I think that's probably enough for you to be able to do your next assignment.